So we're going to consider a cubic example here. Y equals f of x equals x cubed plus x plus 1. If you graph this function, you can go ahead and try it on your calculator. You will see that it's a one-to-one function. This graph is going to look about like this. Being a one-to-one function, it's got an inverse function. If I draw the diagonal line y equals x and reflect the graph of y equals f of x across that diagonal line, I will get the graph of the inverse function. Right? It's one-to-one. It passes the horizontal line test. No horizontal line goes through it more than once. Therefore, when you reflect it, you'll get a function that passes the vertical line test. No vertical line will go through it more than once. And that means it is the graph of a function. Y equals f inverse of x. What's the formula for that function? That's pretty hard to find out. We will have Mathematica see if we can find it out for us, but we're going to do something that can be done without Mathematica. What I'm interested in is seeing if I can figure out the slope of this green graph at the point with coordinates 3, 1. Can I figure out the slope of that green graph at this point with coordinates 3, 1? How do I know that point, first of all, is on the graph? Because when I plug 1 into the function over here, with that formula, I get 1 cubed plus 1 is 3. That means the point 1, 3 is on this graph. And since the inverse function is the reflection across the line y equals x, that means the symmetric point across that line, whose coordinates are the original coordinates swapped, is on the graph of the inverse function. My goal is, what is the slope of the tangent line to the inverse function right there? The slope equals what? Question mark. That's what I want to find. Well, if you don't have a formula for f inverse, how can you possibly find it? How can you possibly find that slope? Through the same kind of tricks we saw last Wednesday. F of f inverse of x equals x over the entire domain where f inverse is defined. Well, f inverse is defined everywhere. This is true for all x. Just like last Friday now, we can differentiate both sides of this equation, at least if we assume f is differentiable. Well, certainly f is. It's a cubic. We know cubic functions are differentiable. And if we also just assume f inverse is, that's a pretty big assumption, actually. Though, from a technical standpoint, though it should seem reasonable. If the black graph is smooth, its reflection should be smooth. No corners in it, and also no vertical tangent lines. So differentiate both sides. I've got to use the chain rule on the left side, right? I've got an inside function, the unknown inverse function, and an outside function, the original function. That's a composition. I've got to use the chain rule. Find the derivative of the outside, plug in the inside function, then multiply times the derivative of the inside function, f inverse prime of x. And I did not make any written typos there. That is the right way to write the expression there with parentheses where they should be. That's the derivative of the left side. The derivative of the right side, x, is just 1. This is useful because now I can just solve for the unknown inverse function derivative. Divide both sides by that derivative. Therefore, f inverse prime of x is 1 divided by f prime of f inverse of x, at least as long as I'm not dividing by 0. As long as we are not dividing by 0. Now, it's actually possible that you'd be dividing it by 0 at some points, but in this problem, we're not going to be. We're not dividing by 0. How's that helpful? I want to find the slope of the inverse function at this point where x is 3. Just plug 3 in here. Therefore, for our problem, f inverse prime of 3 is 1 divided by f prime of f inverse of 3. But how is that helpful? Doesn't look very helpful, does it? We can do this without coffee, okay? Take a breath. Take a breath. We can do this without coffee. Just realize I've got to find f prime, and then I got to plug f inverse of 3 into there. Well, f prime is easy. F prime of x, I can just differentiate the original function, is 3x squared plus 1. But what's f inverse of 3? Right there. How do I find that? The answer is somewhere in the picture. What's f inverse of 3? Look at the picture. It's 1. Second coordinate of this point. This green graph is f inverse. I know the point 3, 1 is on it because 1, 3 is on the graph of the original function. I know for f inverse of 3 is 1. This is 1 over f prime of 1, amazingly. And again, here's f prime. So I get 1 over 3 times 1 squared plus 1, 1/4. That's the answer. So we did it. It's a line with a slope of 1/4, and I could then use that to figure out the equation of the tangent line there. Let me go ahead and do it just for the sake of completion. Lots of arrows going all over the place. If I go back and use the slope of 1/4 to find the equation of the tangent line right there, using, say, point slope form, I can say it's y minus 1 equals 1/4 times x minus 3. Solving for y, I can say y equals 1/4 x minus 3 plus 1. I can expand that to slope-intercept form if I like. Let's go ahead and do it. Y equals 1/4 x. We'll get a minus 3/4 and a plus 1 gives you plus 1/4. So this green line has a slope of 1/4, and it also happens to have a y-intercept of 1/4. Something else special about this is you could use this green line, this tangent line, to approximate f inverse when x is close to 3. For example, I could say, didn't give myself enough space, f inverse of 3.1 would be approximately equal to what I get when I plug in 3.1 into this tangent line formula. It's actually simpler to plug it into this one, where I'm pointing there. If you replace x with 3.1 right there, 3.1 minus 3 is 0.1, times 0.25 is 0.025, plus 1 is 1.025. The point with coordinates 3.1, 1.025 is exactly on the tangent line, approximately on the curve, because they're close together.